So my name is Weili. So I'm currently a fellow year PhD student at Rice University. And so my PhD study has been focused on generative models, disentanglement learning, and visual reasoning. So these are tasks. And during my PhD, I have been working as an intern, so a long-time intern, like 1.5 years at NVIDIA. And I'm going to graduate, so I expect to graduate in December this year, so very soon. And then after that, I'll join NVIDIA as a research scientist and continue working on disentanglement learning and visual reasoning. Yeah. Okay, so today I'm going to present our ICML 20's work, Semi-Supervised StyleGAN for disentanglement learning. This work is my internship work at NVIDIA, working with Taro, Animesh, Sobik, Anuj, and Anjun, and Anima, and also my advisor, Ankit. So for this talk, feel free to interrupt me and ask questions if you have. Okay. So first, why we need disentanglement? Because we humans can learn and combine factored and semi-semantic consistent representations. And we hope disentanglement learning can simulate this process. So this figure shows a pipeline for disentanglement learning. So it includes two parts. The first part is learning disentangled and interpret representations. So basically, given image, we want to infer its fact code. For example, here, given a car image, we can infer different attributes like identity, pitch, elevation, and all this attribute has been represented by a fact code. And then in the second part, the controllable generation part, we want to combine different values of this fact code to get a new fact code, and then pass into a generative model to generate a new image, like a new car here, which has never been existing in the training set before. So we can see that disentanglement learning actually can match human experience of learning and imagination. So for example, many of us may have not seen a red dog, but we can easily imagine a red dog in our brain. And disentanglement learning can be good for many downstream tasks, good for compositional generalization, model interpretability as well. So we can see that in this empirical slide that there are many two objectives in disentanglement learning. The first one is to learn disentangled and interpretable representation. The second part is controllable generation. So with these two objectives, so currently there are two main branches of disentanglement methods. The first one is VAE-based disentanglement methods. The representative one is beta VAE, and the second branch is GAN-based disentanglement methods, and the most representative one is the InfoGAN. So next, I'm going to give some background and beta VAE and the InfoGAN, and then come to our work. So first, beta VAE. Beta VAE is a modification of traditional VAE with a special emphasis to discover disentangled latent factors. So here is the original VAE loss, which is an ALBO, evidence lower bound. And in ALBO, it includes two parts. The first part is image reconstruction term. And this part will be mainly responsible for image generation quality. And the second part is a KL term and approximate posterior. And this part will be corresponding to the disentanglement performance. So in beta VAE, their modification is very straightforward. So they just add a new hyperparameter beta to balance these two terms. So when beta is 1, then beta VAE just reduced to original VAE. And but interestingly, when we increase beta like greater than 1, we can achieve better disentanglement performance than original VAE. So here they show some results comparing beta VAE and VAE. So the first two the left two blocks are the results of beta VEs, and the right two are results of original VE. So they show rotation and smell. So we can show that so beta VE can achieve better disentanglement. So when they change each factor, the other factors does not change, but for VE we can see some other like a disentanglement issue. And the second one is InfoGAN. InfoGAN modifies, so their goal is to modify the original GAN objective to encourage it to learn interpretable representations. So their basic idea is to maximize the mutual information between a fixed set of latent code and observations. So we can see here, the latent code here, they use a C called a fact code to represent the factor of variations. And then they want generated like a G of Z given Z and C to be correlated with this code and to maximize this mutual information. And so in the InfoGAN loss, it also includes two parts. The first part is original GAN loss. So here normally we use cross entropy to represent GAN loss. And the second part is a variational lower bound of mutual information, because the exact mutual information computation is intractable in general. So we have to do some approximation and that. And based on the original InfoGAN work, they have shown that this approximation of mutual information comes to code reconstruction term. So basically they use a new encoder, they call it Q function. So given input image X, they want to infer its factor code and then do code reconstruction. So yeah, so in practice, this new encoder Q shares the most layers except for the last one with the discriminator to reduce the computational budget. And they also show some results like here and MList. So they can vary different dimension of the factor code like C1, C2, and C3. And they can control different attributes of the digit, like digit type, rotation, and width. Yeah. But we have found that there's some like current challenges in disentanglement methods. So the first one is they have difficulty with high resolution images. So here we show that these two like these sprites and 3D shapes, these two disentanglement dataset has been widely used for evaluating the disentanglement performance in current methods. But we can see that here, both this sprite and the 3D shapes, they are just some very simple shapes. And so the photorealism is missing here. And the image resolution is low, just 64 by 64. So to overcome this issue, we propose to like use a stronger generative models to do disentanglement learning. So basically we use StyleGAN as our backbone architecture. And also we want to measure the performance of our methods and high resolution data set, but currently we have no very good high resolution synthetic data set for quantitative results. So then we create this high resolution synthetic data sets. We call them Falco 3D and SX 3D by using NVIDIA graphics renderer. And here we can show like we can see some like two examples of SX 3D and the Falco 3D. So we can see that the photorealism is much better than previous sprite or 3D shapes. And we also compare the statistics of different disentanglement data sets with our proposed. So we can see that our proposed Falco 3D and SX 3D can have much higher resolution, better photorealism, and richer factors of variation. We hope this new data set can demonstrate some disentanglement advantages of our proposed methods and high resolution imaging disentanglement learning. And the second challenge.
I have a question.
Yeah, sure.
So in the previous slide, the number of factors or Because these are synthetic data sets, you know the number of factors, right? And
Yes.
from what I know, isn't car 3D a real like image data set? I know it's like a camera pose changes, but then that doesn't mean those are the only factors changing in the scene. So how does, for instance, how do you know the number of factors of a data set, basically?
So basically, because we use a graphics renderer, right? So we can tune so in the graphics renderer, we have different parameters to tune. We have a camera position, light intensity. So we change this parameter to get a bunch of data set. And this different data set, so different data will correspond different factors because we have the control.
But I'm saying some of these data sets are not synthetic.
Which one?
Like I think cars, maybe it's a different cars 3D, but there's a cars data set, which is actually pictures of cars when the camera goes around the car, like on a moving platform.
You mean the cars 3D?
Yes.
Like, yeah, I think they use human annotation to do that. They do not use graphics renderer. Yeah.
But it's still, I'm not sure if like, when you have two natural images, it's really hard to define what the difference of factors between the two are. You would say that, hey, if the camera pose has changed, it's like 3 degrees of freedom, only camera pose, but then there's like other things that are not out of control, like if the lighting changes and so on. Maybe it's a different car data set, but the car data set that I know of is actually natural images, and it's exactly like 3 degrees of freedom that is observed, that's recorded as the camera pose, but there's other factors in the scene like that it's not recorded. So it's hard to declare that there's exactly 3 factors of variation. It's at least 3 factors of variation, but it's not.
Yeah, that's true. I think, yeah. So each factor code may correspond to different causes, right? But yeah, but in our annotation, especially in the synthetic data set, we can control those. We can deterministics to show that if we only vary these factors, we can get this kind of rendered images without some stochasticity.
Sure.
Yeah.
These the images are the images that you're showing on the left. Are they rendered or they are?
Yeah, they are rendered. Yeah, so we can precisely control each factor.
But are these like the predictions of the disentanglement code, or these are like the rendering of the graphics engine? Like, are these ground truth or are these actual?
Yeah, they are be treated as ground truths.
I see. Okay.
Yeah.
Thank you.
So basically, we want to just it's very similar to inverse graphics. We give the image, we infer its code, and go code back to the image we want to match, predict the image to match the original one. Yeah.
Thank you.
Yeah. So this synthetic data set is it's good for us to prototype the disentanglement learning because we can precisely control the factor code. We precisely know which factor will cause which effect.
And also, shouldn't why Clever is not indexed here?
You mean Clever dataset?
Yeah.
I think Clever dataset, they are more for visual question answering, right? So they have so their supervision is different from disentanglement.
People work pretty frequently for disentanglement. Yeah, it's originally when they proposed it was for like captioning and question answering. But then the same engine and same data set basically people used for because those scenes are synthetic, so that you know exactly the parameters that render the scene. So people have used it for actually. Actually, one of the most used data sets, but you know better.
Yeah, I think Clever. So in terms of photorealism, Clever is not better than ours because they are also just dealing with shapes. Yeah. Okay. So, okay, to move forward, the second challenge for current disentanglement methods is they primarily focus on learning disentanglement representations. As we showed before, there are 2 parts in the disentanglement learning: this representation learning and controllable generation. So basically, previous methods they only measure the performance of an encoder in both VAE-based and GAN-based methods, and the decoder part they do not measure their performance. So we want to. So in our work, we introduced 2 metrics called MH gen and L2 gen just to mimic previous metrics MIG and L2 measure encoder, we use MIG gen and L2 gen to measure decoder. And then we can quantify the controllable generation ability as well. And in fact, we have shown that indeed there's some trade-off between controllable generation and disentanglement representation. We cannot rely on a good representation learning to get a good controllable generation. We have to measure both. Yeah. And the third part is challenging is the non-identifiable issue due to the unsupervised setting. And the previous work from Loctano and others, they have shown that if the model is purely unsupervised without a strong model inductive bias or supervision, then we have some identifiable issue, which means every time when we change hyperparameters of the model or randomness of the model, then we will get a different bunch of factors to capture. So we need human in the loop. So after learning, we need human in the loop to identify what I've learned. But before human do the check, we don't know what I've learned. So this is basically the idea, the issue of identifiability. And even worse, the previous one has shown that this figure that when we're varying randomnesses here or varying the hyperparameter, we call regularization strengths. So varying randomnesses or hyperparameters may lead to substantial impact on the results. Yeah, so basically the model, like a lot of disentanglement tricks, may be dominant by this hyperparameter changing or randomnesses. Yeah, so this is very bad. And in our case, we want to get rid of this non-identifiable issue. So we consider to add some limited supervision and consider semi-supervised setup, and to show how limited the supervision we can need to maintain very good disentanglement performance. All right. So yeah, so because we use StyleGAN as our backbone, so the first question would be why we need StyleGAN for disentanglement. So because disentanglement is because StyleGAN is good for high resolution images, but still we want to show or quantify some disentanglement performance before we move into semi-supervised setup. Okay, so first let me introduce StyleGAN. And StyleGAN basically uses a style-based generator to replace traditional generator. So here is a traditional generator, and we have a latency directly passed into the synthesis network. But in StyleGAN, they have a different setup. The latent code Z is passed into a mapping network and to produce styles, and the styles will modulate each convolutional output in the synthesis network. And the modulation they do is by using adaptive instance normalization. And adaptive instantiation basically to do a normalization across the spatial dimension, and then they use the learned styles to modulate the normalized convolutional output. And hopefully they can, the learned styles can be added into the outputs in different levels. Yeah, so this is the basic idea of StyleGAN. And so by doing this kind of style-based generator, they can generate very high resolution realistic images. And so that's why we use them to do high resolution disentanglement learning. And next in our work, we first want to show if we just combine InfoGAN and StyleGAN without extra tricks for encouraging disentanglement performance, what performance can we get? So basically we just replace original InfoGAN architecture with a StyleGAN architecture, and to test if the StyleGAN architecture is good for disentanglement learning or not. And so we compare info StyleGAN with state-wise unsupervised disentanglement methods and display data sets and SX3D, what we proposed. And for SX3D, because we compare with the previous methods like VE-based methods and InfoGAN CR, and they are not good at generating high resolution images. So in the first, we first need to downsample it into 128 by 128 resolution to make a fair comparison. And we can, for baseline methods, we use beta VE, fact VE, beta TC VE, and InfoGAN CR. InfoGAN CR is a state-of-art info GAN variate method. And for a more, fair comparison, we also reduce the number of parameters in original StyleGAN, because the StyleGAN is a giant model, and there are far more number of parameters. So we want first to create a smaller size version, we call the StyleGAN star, and we can see if for the StyleGAN star, the number of parameters is comparable to the baseline methods to make a fair comparison. And in this sprite, we use a fact score and image to measure the disentanglement performance. We can see that StyleGAN can achieve competitive or even better disentanglement performance than these state-of baselines. And the similar results also appear in the SX3D, which we created. Yeah, so this result showed that the StyleGAN architecture is good for disentanglement learning. And then we can use it for semi-supervised disentanglement learning. And here we show the generation quality of StyleGAN star. So we can see the human evaluation matches the FID score we measured before. And the StyleGAN star is much better than previous methods. So then we come into the semi-StyleGAN, the model we have been proposing in this work. So basically the modification in the network architecture is very straightforward. And we just split the original latent Z into two parts, the fact code and the latent Z. So fact code will be specifically corresponding to the factor variation we care about in the task. And the latent Z will capture the other nuisance in the data set. So the mapping network in the generator condition the fact code, and the encoder predicts its value, and then we can do fact code reconstruction. So this setup is very similar to the InfoGAN setup. The difference is we introduce a new semi-supervised loss to incorporate the supervision. And in this semi-supervised loss, we include 3 regularization terms. We have an unsupervised InfoGAN loss term, and the supervised label reconstruction term, smoothness regularization term. We can see all this unsupervised, supervised, and the smoothness regularization term, they all about code reconstruction. The only difference amongst them is we use different data sources for this reconstruction. For example, in the unsupervised term, we use generated code and images for reconstruction. And the supervised term, we just use labeled observation and the code pairs for reconstruction. And for the smoothness regularization, it's a mixture. It's a mixed set of labeled real code pairs and generated image code pairs. And next, I'm going to talk about how to do this mixture, how to form this mixture set. So in the smoothness regularization term, the observation X and the code C is sampled from the mixture set M. And by forming this mixed set M, we perform a mix-up operation between real labeled data and the generated data. So basically, for the observation, the real observation and the fake generated observation, we just do a convex combination between them. And we do the same convex combination between the real code and the generated code. Yeah. And so this basically is adopted from original mix-up operation. Mix-up is original design for semi-supervised image classification task. And what they do is they perform mix-up this kind of convex combinations between labeled data and unlabeled data. In our case, we are performed between real labeled data and the generated fake data. So this is the difference. And by doing this kind of mix-up operation, it will only encourage smooth behaviors. So then the latent factor, we hope the latent factor position, the space can be smooth enough for better disentanglement performance. And on the other hand, we also can take good advantages of enormous fake data for encouraging disentanglement. So now let me show some quantitative results on StyleGAN. And so we train StyleGAN and StyleGAN with 0.5% of label data. And then we do some latent traversals and different attributes in the face images. So here we show bands, glasses, smelling. So we can see with very limited supervision, StyleGAN can achieve good disentanglement performance and real data. So next we show quantitative results on SX3D. Similarly, we train StyleGAN and SX3D with a 0.5% of label data, and we'll also do some latent traversal and different attributes in the dataset. Like here we show robot X movement, so the robot arm will move from left to right, and the lighting direction. So the lighting, like is a source light. The lighting will move from bottom to top. We can see the shadow also moves from top to bottom. And the object scale, so the object will move, like become larger and larger. So we can see with limited supervision, each factor in the tabulated images changes smoothly without affecting other factors, which means a very good disentanglement performance. And similarly, quantitative results on Falco's radii, another synthetic data set we created. And we train StyleGAN on Falco's radii with 1% of label data and do latent traversals and different attributes. So here we show lighting intensity from weak to strong, and the lighting X direction. So the lighting we can see from left to right, and the shadow from right to left. So, and also the camera position. So when the camera will move from left to right as well. So we can see each factor in the tabulated images changes smoothly without affecting other factors. All right, so next we also show some quantitative results. So first we show the role of limited supervision, and the question is how limited the supervision is to maintain good performance and disentanglement learning. So here we show like results. So left 4 figures are results on SX3D, and the right 4 figures are results on Falco's radii. And in each figure we measure a respective metric. So like MIG and L2, they are used to measure disentangled representation learning. MIG gen and L2 gen, they are used to measure controllable generation. And for MIG and MIG gen, the higher the better. For L2 and L2 gen, the lower the better. And in each figure, the y-axis is the metric score, and the x-axis is the supervision rate. So for example, here, the supervision rate will move from 0.1% to 1%. So we can see in each figure, the dashed lines are fully supervised performance, and the dotted lines are fully unsupervised performance. And the solid lines are what we propose semi-StyleGAN performance. So we can see that by only using 0.125% to 2.5% of label data, we can achieve nearly fully supervised disentanglement performance. And we also do some ablation studies. So we first we modify different regularization terms in the loss function to show their impact. So for example, here we remove the smoothness regularization term, and we can see in both cases, all the scores, they're getting worse, which means this smooth consistency term is can benefit the semi-supervised disentanglement learning. Now we're also trying to modify the unsupervised regularization term in both encoder and generator. So we can show that here, for example, a better MIG and L2 score does not always come with a better MIG gen and L2 gen scores. So which means better disentanglement performance, better disentangle representation learning performance does not always come with a better controllable generation performance. And in the extreme case, if we remove the unsupervised term in generator, we can still get some decent MIG and L2 score here, which means a decent representation learning performance. However, the MIG gen and L2 gen score, they are just like a performance of a random untrained network, which means the controllable generation is like a failure. And so this means that, so this results means that there may exist a trade-off between controllable generation and disentanglement representation learning. So we hope the disentanglement methods can strike a better trade-off for this both performances. So in the next, we consider to like some generalization performance. So we propose semi-StyleGAN fine by modifying the architecture for semantic fine-grained image editing. So the motivation is, as I just said, we want to extend semi-StyleGAN for better generalization to unseen images. Because for semi-StyleGAN, the results we have shown that if the semi-StyleGAN is basically is how to say is unconditional generation, we cannot say some like a generalization ability. So what we want to do is we want to like how if we can fit some like novel imagery that have never been existing in the original data set into the generator, can we use the learned factors to modify the original the new images to show some generalization ability and to demonstrate that your disentanglement performance can generalize well. So this is basically our motivation. And what we do is now the generator will take a new image as input. So in the generator, we first remove 4x4 up to 32 by 32 blocks. And then we downsample real image into 32 by 32 resolution. And the downsampled real image will pass into a new input block. And then this is what we do for the generator. So the generator can take real image as input and modify the real image along its super resolution process. And in the discriminator or encoder, we are going to output this fact code from the 32 by 32 block instead of from the final block as we did in the semi-StyleGAN. The reason is because if we only care about fine-grained factors, the only high resolution blocks in the discriminator are responsible for the prediction. So we don't need to go down to the top. So two things to remember here is we keep the loss function to be the same with semi-StyleGAN. And this generalization performance basically is compositionality between the learned fine-grained factors and unseen image content. So here we show some generalization and syllabi. So basically, we train semi-StyleGAN and syllabi with 1% of label data, and then we random choose some deep learning researchers as test images, and then we apply the learned factors into these new images by doing some latent traversals. So here we show bush eyebrows, slightly open mouth, low beard. So we can show that these learned factors from syllabi can apply to the new test images, which have now been seen in the syllabi dataset. And also for the SX-ready, we also did the same generalization testing. So we train semi-StyleGAN fine as SX-ready with 1% of label data. And then to collect test images, we do two things. We first shift the robot position to the right-hand side a little bit and attach it with an unseen object. So this object have never been seen in the training set. So we can see the lighting intensity, object color, or color. These learned fine-grained factors can be applied to this new test images with a novel object and a novel position of the robot. And these results demonstrate a good generalization ability of fine-grained image editing. So takeaways: only limited supervision can significantly benefit disentanglement learning, and we don't need to suffer from non-identifiable issue anymore. And also the second one is a good disentanglement methods need to strike a better balance of disentanglement, representation learning, and controllable generation. And so in this part, I have to say that depending on your downstream task, if your downstream task is better, is just for representation learning, then you may emphasize more and disentanglement representation learning ability. But if your performance is about controllable generation, then you have to focus more on that part. Yeah. So finally, also there are some limitations of our work. I think can serve as a very good follow-up of work for future. So for example, we rely on limited supervision, but the limited supervision is very strong. For example, for the StyleGAN, we use even though we use 0.5% of label data, but for each label, we need 20 attributes to be fully represented, with absolute value. So there are some recent work they trying to overcome this issue. For example, they propose to do weakly supervised or semi-supervised weakly supervised, this kind of extension. And the second is we are far from the perfect disentanglement quality. So even though I have shown some good performance, but we can still see some small confounding factors make our disentanglement traversal not perfect. So we think if we can add not just supervision, if we can add some strong inductive bias. So for example, if we want to do 3D rotation, maybe we can add some 3D rotation, this kind of inductive bias or we can add some causal structure in the latent space to further make a disentanglement performance better. And the third part is there exists algorithmic bias like a race and gender. So and this had never been existing in the synthetic data set, but when we apply this our semi-StyleGAN or semi-StyleGAN find to StyleGAN, because StyleGAN is there are a lot of imbalance between attributes. Like female the female images are more than male images, and the race have some imbalance. So we can see that in some underrepresentative attributes, if we do latent traversal, the performance is way worse than other overrepresented race or gender. So we hope to do some fair generation into the disentanglement learning to overcome this algorithm bias. Yeah. So that's it. Any question?